All right. Welcome back, everyone, to the second interactive session of the course Viscous Fluid Flow. We'll just wait for a couple of minutes to see if anyone joins, or like we will start with the contents that we are supposed to discuss in this session. Yes, this is fine. Okay. In the meanwhile, I'll just check the recording. Okay. Recording in progress. That's fine. Okay. Okay. All right. Once again, welcome back. So this is week two, and we finished discussing. So in the last week, we discussed something which is known as. So we basically looked into the fundamental definitions of fluid dynamics. So it's a startup of basically the course that we are supposed to. Uh, so we are supposed to look at in this sessions of the course. So we looked into something which is known as the Reynolds transfer theorem. And if you remember, so we argued that it's just a bridge between something which is known as a control mass system, and it links to the control volume system, which is the favorable analysis that we do as fluid dynamics. The reason, again, we attributed to the fact that most of the laws of nature, for instance, the three basic laws of Newton, or similar laws, these are written for Lagrangian these are written for Lagrangian frames, or Lagrangian descriptions, to be precise. But it is more easier in fluid dynamics to deal in uh, Eulerian descriptions. Typically because, like, as we said, that since Lagrangian description relied on just we just need to focus, or we just need to shift our attention to just one fluid particles, which is not the case in case of Eulerian descriptions, where we fixed our attention to a given space instead of just tracking one fluid particle that is in motion. This is typically because there are millions and billions of fluid particles that that are generally in motion when we talk about fluid mechanics. And for us, unless and until there are some special requirements, it is more easy to deal in, or to stay in Eulerian descriptions than to be in Lagrangian frames. So this is something that we saw. But in and also we looked into something which are known as streamlines, and we said that and we basically found out a way to evaluate the streamlines given we have the velocity field in an Eulerian frame, as we saw in one of the representative examples. For instance, if I correctly remember, we were asked to basically evaluate the stream function from this given velocity field of interest. And we saw that when we define stream function, the continuity equation was trivially satisfied, and this comes from the very definition of the stream function of the stream function, which basically tells us that the way we define stream function, the continuity equation is just trivially satisfied. That is something that we saw. And towards the end, we looked into something which is known as the velocity potential, and we said that if the flow is we argued that if the flow is basically irrotational, then we can irrotational, meaning that the curl of velocity is zero, then we can say that then we can actually write velocity as a gradient of a scalar function, and that scalar function we talked about it as the velocity potential. And then we said that if the flow is incompressible and also it is irrotational, then the velocity potential satisfies to something which is known as the Laplace equation. And and we saw that the Laplace equation is an interesting, and it's I would say it's kind of a very definitive kind of I would say it's kind of a very definitive kind of an equation in fluid mechanics, or in mathematics, or in any other branch, typically because there are certain reasons. For instance, we looked into so we argued that the solution to the Laplace equation are known as harmonics. And Laplace equation and its solutions, so the solutions that we get by solving the Laplace equation, they are kind of an averaging functions, meaning that we cannot have a local minima or a local maxima in the solution of Laplace equation. So these are some useful characteristics of Laplace equation. And also, although I didn't write, I So there are something which is known as uniqueness theorems in Laplace. So there is something which is known as the first uniqueness theorem, which says that in a given space, in a given volume, okay, if I want to calculate the solution to a Laplace equation, its solution could be uniquely determined if I specify the value of the function at the boundaries. Okay, and this and this theorem, which is known as the first uniqueness theorem, there is also something which is known as the second uniqueness theorem. We'll not go into the details of this, but because that is beyond the scope of the course that we are currently dealing with. But all these uniqueness theorems comes from these characteristics of Laplace equation that we basically saw. Okay, so this is something that we saw in the last class. However, there were some confusions related to the Eulerian and Lagrangian descriptions, and today, before going into the contents of week 2, we will quickly look at a sum or a problem that involves in this Eulerian and Lagrangian code. I mean Eulerian and Lagrangian descriptions, uh, which I guess will clarify the doubts which you had in which some of you had in the last week. Okay, so we'll do that. So that's the agenda. We'll do this problem, and we'll not spend much time on this because we have many more things to cover today. But we'll solve this problem, and this will help us to get an understanding of the two descriptions, basically the Eulerian and the Lagrangian descriptions. And then we will proceed with the discussions of week 2, which basically is the central theme of this session. Okay, but before that, I want you to read this problem. So it's basically, so I call this problem particle acceleration in Eulerian and Lagrangian descriptions, and it just says that it's a very simple problem. It will give you a flavor of how these two descriptions work, and also it will clarify you so if there are any doubts in distinguishing between these two descriptions, it will undoubtedly clarify the doubts that you have. Okay, so it says that there is a channel of this form. So this is not just so this channel is not just, sorry, so it's just not a straight line. You can assume that the flow is taking place along this x-axis, given that the channel dimensions and all those things are known. So what they're saying is that the center line velocity of the flow is given to be some constant into 1 plus x by L, where L is basically the length of the channel. Okay, so this is something that they have given to us, where this v1 is a constant, L is the length of the channel, and the flow, as you can see, is necessarily unidirectional, because we just have an x component of velocity in the flow field. So first of all, given this information, what they are asking us to find is, they're asking us to evaluate the acceleration of a particle moving along the center line. That is, if there's a particle that is moving along the center line using the Eulerian approach and the Lagrangian approach. So these are the two things that they are asking us, and based on the flow field that they have given. But as I repeatedly said, you need to understand that the flow description that we are given here, this is an Eulerian description, typically, because as we have seen it repeatedly, that the velocity field is just a function of space, which means it's a steady Eulerian description that we are looking into the problem. So given this scenario, and given this context, what they're asking us is that first you need to calculate the acceleration using the Eulerian approach, and then you need to devise a strategy to find out the acceleration given this Eulerian velocity field using the Lagrangian approach. And towards the end, we'll prove that either you follow the Eulerian approach and the Lagrangian approach, the acceleration is a physical quantity, right? In whichever approach you follow, you can prove that this acceleration is essentially the same, and this we will do it towards the end of solving this problem. But yeah, the first step is to evaluate the acceleration using the Eulerian approach given this velocity field, okay, which is of course unidirectional, as I said. And the second task for us that is in our hand is to think about a strategy to evaluate the acceleration of the fluid particle, because now we are in Lagrangian frame. Okay, given this velocity profile that is given to us. Okay, so I'll stop here for a couple of minutes. You can have a look at this problem, and if you want to speak out, or if you want to have certain ideas on how do we go ahead and solve this problem, please feel free to let me know. Okay. Yeah, so for the ones who joined late, so I'll just summarize. So what we are doing is I was just giving a recap of the of the things that we did in the last session. Uh, so basically we looked into something which is known as the Reynolds transport theorem and looked into some basic definitions of fluid dynamics. That is the streamlines, the stream function, the velocity potential, and what happens when a flow is irrotational, what happens when a flow is incompressible, and so on and so forth. Okay, but since there were certain doubts involving the Eulerian and Lagrangian descriptions, before moving into the discussion of this second week, which we will do today after like in some time from now, I want you to basically solve this problem, which involves the basic description. So it's just the prototypical problem which gives you a flavor of how these two descriptions work, the Eulerian and the Lagrangian field. Okay, and for that, this is the problem at your disposal. You can so I guess you can have a look in my screen, and you just need to basically do this. So you just need to calculate the acceleration given that we have this velocity field, which is an unidirectional velocity field, as you can appreciate. You need to calculate the acceleration using the Eulerian approach and the Lagrangian approach. So these are the two things that we need to do. So any suggestions like how do we do this? At least the first, I guess the first part is simple. Uh, how to basically calculate the, because this is something that you already did in your first assignment. So can you tell me how do we calculate the Lagrangian, sorry, the acceleration using the Eulerian approach? Uh, I believe you have understood the problem, right? I mean, at least that part is clear. All right. So okay. So I'm taking it for granted that you have at least understood the problem. So we'll go ahead and we'll try to solve this. Uh, So let's get started. So first of all, let's do the easy bit first. So we will try to find the acceleration of the. We'll try to find out. So it's not so since we are in since the first problem demands us to calculate the acceleration in Eulerian description, we will not call it the acceleration of a particle. Rather, we'll call it that since given the velocity field, we'll try to calculate what is the acceleration field basically. Okay, using the Eulerian approach. Okay, so let's begin. So so if I use the Eulerian approach, given that I know the velocity field, which is basically this, okay, and from here, since the velocity field is a unidirectional velocity field because it just have a magnitude of v1 into 1 plus xl. This is the magnitude of the velocity field, and the direction, the unit vector is along the x direction, where e hat x is the unit vector along this x direction precisely, which means I just have the ux component of velocity field, which is just this, and the other component, which is uh, which is uy and uj, these are precisely zero. I hope you can appreciate this fact. Okay, so given this, using the Eulerian description, the okay, acceleration, I'll write it first in the vector form because of the fact that acceleration, since velocity is a vector, of course the acceleration will also become a vector. So the acceleration in Eulerian description will basically look something like this. So this is something that you have already seen in the theory classes, and you have done problems, repeated problems on this in the assignment. So the acceleration will look like something like this. So it will have the temporal term, which will be just the temporal variation of the velocity field with respect to time, which is just del u by del t, plus the convective term, which you guys know it is just so I guess I denoted velocity with v, so I'll just denote it as v, and the convective term would be v dot del v. That's it. So this so in Eulerian description, this the total. So can you tell me what is the combination of these term and these term is known as? So this is called as the temporal derivative. So I hope you guys know these things. This is called as the temporal derivative. This term is called the convective derivative. Sorry. And the sum of the temporal and the convective derivative is usually denoted by something like this. And this is known as material derivative, which you guys are much familiar in the Eulerian system of description. Okay, so this is known as, this is known as the material derivative. Okay. All right. So now it is easier for us because since we just have an ux component of velocity, so the axis. So if I write this vector form in component wise, I will just have an acceleration in the x direction because uy and uz, which are the y and z component of the velocity field, are essentially zero, which means that the acceleration corresponding to the y and z direction will also be zero. So I'll just have an acceleration in the x direction, which means that my ax, I mean, I guess you are with me on this so far. So my ax is just going to be del ux by del p because of the fact that my v is just this ux times ex, and that's it. That's the only velocity field and the only component of the velocity field that we have in this problem. Okay. So my ax is going to be del ux by del p plus ux. So if I just expand this term, it will just become ux del ux by del x plus Vx, okay, del Ux by del y. This would be, I'm sorry, this would be Vy, or it's better to write Uy, just the notation. So it is Uy del Ux by del y plus uh, Uz del Ux, okay, by del z, where this Uy and uz, these are the y and z component of the velocity field, which we don't have in this problem, which means that these terms are straightforward. So these terms will just are just zero, that's it, because of the fact that we just have an ux component of velocity and we don't have uy and uz. Okay, and also it is important to note that the velocity field that they have defined us is a steady velocity field, meaning that the velocity field is independent of the time variable, which means that this term will also be equal to zero. Okay. So we are just end up so we just end up having ax as ux into del ux by del x. That's it. And we know that our ux, which is the x component of the velocity field, is just this. It is just v1 into 1 plus x by l. Okay, so ux is just v1 into 1 plus x by l, where the l is a constant. It is just the length of this channel. So this is just l. So this is just L, which is a constant, of course, because the channel length is, of course, constant. Which means if I just calculate, and V1 is just the magnitude, okay? This V1 is also it's just the magnitude. That's it. Which of course is another constant. Which means if I calculate this term del ux by del x, because I need it here, so this del ux by del x is just V1 by L. Okay, so if I just put this term into the expression of ax, then my ax simply turn out to be what? So it just turn out to be ux, which is v1 into 1 plus x by l times del ux by del x, which is basically v1 by l. Okay, so if I just calculate my ax, which is the acceleration in the Eulerian description, is nothing but v1 square by l into 1 plus x by l. That's it, guys. So this is precisely the acceleration that, so this is the acceleration field that we calculated from the velocity field in the Eulerian description using the concept of something which is known as the material derivative, which we just saw here. Okay. I hope you are clear and with me so far. So now a little bit, I mean, that I would say the tougher part, comes into the picture. So so what they now want us is, so I hope this is clear up to this point. There is nothing fancy or there is nothing much tougher algebra that is involved until this point. So now what they want us is, in the Lagrangian frame, in the Lagrangian description, they want us to calculate the acceleration of a single, fluid particle. That's what they want us, given the description of the velocity field that they have given us in the question. So in Lagrangian frame, so now we will calculate acceleration of fluid particle in Lagrangian description. All right. Okay. Any idea on how do we go ahead and how do we solve this? Okay. So here is the thing. So what do we have at our disposal? All we know is a velocity field in the Eulerian description. Okay, because it is given that in the question, it is given that my V is basically V1 into 1 plus x by L. Okay. Of course, we have the unit vector Ex. All right. But you can appreciate that this is an Eulerian description, right? Because of the fact that so what does this give us? This give us the knowledge of the velocity field once we fix the position, which is x. For instance, if I put x to be equal to, let's say, L by 2, it just gives it. So this bit just gives me what is the velocity field at the mid channel length, which is basically L by 2. Okay. So this is essentially and purely an Eulerian description. But we'll so what we will do is we will look this Eulerian description. So we'll recast this Eulerian description in a Lagrangian description in a Lagrangian frame. And how we will do that is something like this. So we can write this. So we can write this velocity field as V, which is the field, of course, and v1 is just a constant, so it is not going to bother us, plus 1 plus this x, which was the location. So x, so what is x? It is the location of any distance in the pipe, basically, or in the channel which we were given. And this location now I can write it as xp of t, where this xp of t, instead of now becoming a location in the pipe, this denotes the location, the x coordinate of a single fluid particle. So this xp of t is the x coordinate of a single fluid particle. And you should realize that this x coordinate will inevitably now be a function of time. Okay, because of course the x coordinate, so a single particle will now no longer be stationary. It will basically move along the center line. Okay, and of course, since this is the center line velocity that they have given us, it is the fluid particle that is situated in the center line of the channel. And since it will move along the center line because there is a velocity field, this means that the x coordinate of a single fluid particle p, so xp denote the x coordinate of a single fluid particle p, and it will inevitably be a function of time, because of course there is a flow due to which the particle will basically move. Okay, so this is how we have recasted an Eulerian description into a Lagrangian description, just for the sole objective to calculate the Lagrangian velocity and the Eulerian velocity. Okay. All right. And sorry, so the objective is to calculate the Lagrangian velocity, and from then we will calculate what will be the Lagrangian acceleration, which the question have asked us to do so. Okay. So I hope this is clear. I'll stop here for a couple of minutes. If you have any questions on this, you can ask me that how did we basically wrote, so how did we basically wrote this from this point. Okay. In the meanwhile, I'll just finish this. So this is just xpt. L is just a constant, so it will just be a constant, and that's it. So this is precisely, so I'll write it. This is precisely now the Vp, which is the velocity of a fluid particle, which is now a function of time, you know in terms of its location, which is xp of t. Okay, so this vp of t, as I said, this is the velocity of a single fluid particle p. And now you can appreciate that since I said this repeatedly in the last class, the Lagrangian descriptions are just a function of time, and that's why you can see that the x coordinate is also a function of time and the velocity is also a function of time. Okay, I hope you are clear on this point. Any questions, you can just feel free to stop me at any point of time and just raise your doubts. Okay, all right. So now the objective is to calculate acceleration, but this doesn't give us acceleration, right? This just gives us a link between what the velocity of the particle would be with respect to its coordinate x. So what we will do is, first we will try to calculate what will be this xp of t, and then if we know xp of t, acceleration is just the double derivative of xp of t with respect to time. That's it. So the first objective, I repeat, since we don't know what is the acceleration, so this doesn't give us the acceleration, right? But what we can do is we can calculate what will be the xp of t, and from this xp of t, we will its double derivative will give us the acceleration in Lagrangian frame, which will inevitably be a function of time, as we will see. Okay. All right. Any questions on this? Okay. If no questions, so now tell me, how do we write vp of t in terms of xp of t? Any idea? In Lagrangian description. And remember, Lagrangian description is a control mass description. It just speaks about particles. Okay. So it's very simple. It is just the equation of motion that we need to write, because we know that Vp of t is what? It is the velocity of a fluid particle with respect to time. And it is nothing but, it's just that it is nothing but the rate of change of the x position of the particle with respect to time, which is nothing but dxp of t by dt. That's it. It's the simple relation between velocity and displacement. That is, the rate of change of displacement is velocity. That's all. That's what we are kind of doing here. Okay, which means I can now write this. If I just substitute this here, I can now write this as what? I can just now write it as dxp of t by dt. See, the objective is to evaluate xp of t, because if we know xp of t, its second derivative will give us the acceleration precisely, and that's what we are trying to do. Okay, so this is dxp of t by dt, and this becomes what? This becomes v1 into 1 plus this is what? This is xp of t by L, and this. Okay, all right. So what I can do is see this is, so as you can see, this is a differential equation. Okay, so the dependent variable is xp of t, the independent variable is time. So we'll just need to integrate this differential equation to basically get xp of t. That's the same. That's all that we need to do here. Okay, so we'll just kind of simplify this such that the integration becomes easier, and we can do some standard integration to basically look at what is xp of t from this expression. Okay, so what I'll do is this term I'll just write it as dxp of t by dt, and I'll just so I'll take L common, which will become not common. I mean, we'll take L in the denominator, and this will become L plus xp of t. And then what I can do is I can bring this L plus xp of t here, and I can bring this dt here, and this is known as separation of variable in mathematics. So we'll just, so what I was trying to do is I'll write it here. So we'll integrate using separation of variables, and I hope you are familiar with this technique of integration. Okay, so I'll bring this L plus xp of t in the denominator, and dt will basically go there, because v1 and L are just constants. Okay, and they will not just bother us in this integration. So this dxp of t by L plus xp of t, and this just becomes v1 L dt. All right, and then we'll just integrate. So we'll integrate this. So we'll integrate from time t equal to 0, and when time, and at time t equal to 0, we'll assume that xp was, so xp of t is 0. Basically, the x coordinate of the particle starts from the origin. That's the thing that we are assuming here at time t equal to 0. And at time t equal to t, the particle is at some xp. Of course, this is a function of time. And then this is just the integration that we need to do. So this is of the form what? This is of the form ddx of, like what? ddx of L plus x. Okay, so this will inevitably give you ln of L plus x. That's the basic formula for integration of these forms. So this will just give you ln of L plus xp of t. I hope you I hope you can just recollect it. This is the basic rule of integration of these of functions of these form, basically 1 by, so it's just that we have a function of these form dd integration of 1 by x dx, which is just ln x. That's it. So if this is ln x, then integration of dx by x plus c, which is where c is a constant, is just ln of x plus c. That's all we are doing here. Okay, and this, since this is a direct integration, it will vary from 0 to some xp of t. And this is simple because we just have a constant which will come out of the integral, and it is the integral dt where it varies from 0 to t, which will just give you t. That's it. So it will be v1, this should be just v1 times t by L. And this will also vary from 0 to t because we are integrating it directly. Okay, so that's it. We just now need, so again, the objective is to basically evaluate xp of t. So that's all that we are trying to do here. So if we just put the limits, it is just going to be ln of what? L plus xp of t minus ln of L, because this limit is equal to 0, and this would be v1 t by L, because once again it is t is 0 at the first instant. That's the thing. Okay, and now this can be written as, so ln of a minus ln of b is ln of a by b, so we can write it as ln of x L plus xp of time by L. Okay, and this is just v1 t by L. All right. So from here, again, the objective, you must remember, the objective is to just find xp of t. So what we'll do is, we'll just take all these things there. So this will just give you what? It will just give you L plus xp of t by L, and this is exponent of v1 t L. Okay. So from here, if you calculate xp, you will see that your xp just comes out to be equal to L times, exponent of v1 t by L minus 1. That's it. So this is precisely how the x coordinate of the particle would basically vary with time, and you can see that it does indeed vary with time. That's it. And so this is how we deal in Lagrangian frames, because the variables are just a function of time, and this shows that the x coordinate of a particle p as a function of time varies something like this in the Lagrangian frame. But remember, we are not done yet, because this is just how the x coordinate basically varies with time. But we need to calculate the acceleration of this fluid particle. Now that is easy, because we know that the acceleration ap of t, which is the acceleration of the fluid particle p, once we know how xp of t varies with time, the acceleration, again, we'll just use the equation of motion. Ap of t, which is the acceleration of the pth fluid particle, is d2 xp by dt square. That's it. It's the second derivative with respect to time. And if you do this, you can just do this second derivative. So just differentiate it twice. It's very easy. You will see that it just becomes v1 square by L exponent of v1 t by L. That's it. So this is precisely your acceleration of you know of the fluid particle uh, in Lagrangian description. So this is just v1 square L exponent of v1 t by L. And you can also appreciate here that your acceleration is indeed a function of time, which is always the case in case of Lagrangian description. So I hope the things that we saw in the last class, this indeed holds true by just solving this prototypical example. That's it. Any questions on this? So these are the things that we are asked to find, that what will be the acceleration of the particle with in Lagrangian frame, which is this, and this is the acceleration of the particle in Eulerian frame. That's it. Any questions? So I hope through this exercise, it has now gave you a clearer idea on how to basically distinguish things in the Eulerian description and to that of the things in the Lagrangian description. Okay. All right. I'll stop here for a couple of minutes and then we will start off with the agenda for this week. But any questions on this, please let me know, and please feel free to, please feel free to, ask. All right. If no other questions, and as I said, like if you have, if you are watching this video, I mean later on in this week through the recordings, as I said that if you have any questions, feel free to uh, post them in the what you say in the Q&A of the website, that is the discussion forum. And as you have already saw that we have at least addressed all the doubts that were there in the discussion forum, and we will continue to do so once and as and when you post your questions in that. So as I said, please actively participate in the discussion forum, and we are always there to basically address your doubts in that context. Okay. All right. So if no questions, so we will start with the agenda for the second week, which is nothing but deriving closed form solution of the much celebrated and a much studied uh, one of the much studied topics of in fluid dynamics, which is the Navier-Stokes equation. Okay. So we'll begin by actually understanding how the Navier-Stokes equation looks like, and this is something that we have that you have already saw in the in this week's lecture series. But uh, as a as a quick recap, we will see what basically the different terms in the Navier-Stokes equation look like. And although at least by now you have appreciated the fact that deriving closed form solution of the complete Navier-Stokes equation is next to impossible, at least as of now. I mean, if there are continuous researches that are going on in trying to derive exact solution to the Navier-Stokes equation, to the full Navier-Stokes equation, but there hadn't been any successful attempts, at least to this point of time. But having said that, if you make some underlying assumptions, uh, deriving closed from analytical solution is indeed possible. And you have already seen that through two through two problems, or I would say like through two nature of problems. One of those problems is known as a Couette flow, where the flow is basically unidirectional and it is driven by the motion of a plate, which basically moves in just one direction with some given velocity. Based on this, of course, it's a steady system that you saw. Based on this, you have essentially derived the closed from solution of the velocity profile using the Navier-Stokes equation in that context. And the second thing, which is the second example of a unidirectional rectilinear flow, to be precise, is a plane Poiseuille flow, or sometimes it's it is sometimes, or it is more commonly known as flow between two parallel plates. It is also known as a plane Poiseuille flow. Okay, so these are the two examples. So these are the two examples that you that you saw in this week. And today we will begin by understanding what essentially, or what different terms in the Navier-Stokes equation essentially looks like, and we will use the Navier-Stokes equation to solve at least one problem involving these two unidirectional rectilinear flows. Okay, and and this essentially will give you clarity on certain problems that are there in the assignment, and as and when there are certain clarifications that are needed to be made in these problems, I'll pause and let you know that let you know the nuances of these well, what I would say of these discussions. Okay, so that's the idea. I'll stop here again for a couple of minutes. If you have any questions, you can ask, maybe a minute or so, and then we'll begin by trying to understand the Navier-Stokes equation and then solve a problem involving this plane or involving this Couette flow and plane possible flow. And through these problems, we'll also try to understand certain nuances of the descriptions, which will again assist you in solving the assignments that you are given for this week. So that's the idea. I'll stop here for a couple of minutes. You can, if you have any doubts, feel free to feel free to ask and let me know. All right. In the meantime, I'll just fill my mug with some water. Just give me a couple of minutes. That's it. And also, if you have any doubts, you can think of it now. Okay. Sorry for the interruption. Okay, so let's get started. So as you know, as you have derived, so actually you can derive the Navier-Stokes equation from the Reynolds transport theorem. Just take the extensive property to be momentum, which means that your intensive property becomes your velocity, and if you just you know substitute that in the Navier-Stokes equation, do all sort of analysis. So okay, you can, and at least you have done this. I mean, you saw this in the lecture classes of first week. You can basically go ahead and derive something which is known as the Cauchy momentum equation, and then if you use Newtonian relation that your stress is just two times of your stress is just two times of the viscosity of the dynamic viscosity times the strain. That's the Newtonian relation that you use. So if you use that and substitute this in the Cauchy momentum equation, you can so the ultimate step is that you get the Navier-Stokes equation. But we will not do this derivation now, because you have already seen that in the lecture series. What we will do is we will start off by writing the vector form of the Navier-Stokes equation, and you know we will analyze what different terms in the Navier-Stokes equation essentially mean. Okay, so the so I will write it as the NS equations, which means the Navier-Stokes equations. So vectorically, this equation looks like rho times the material derivative of velocity, which is dv dt, and the right hand side is something which is known as the pressure gradient, which is gradient of P plus mu del square V plus rho V. So this is the full Navier-Stokes equation, written for an incompressible fluid, uh, considering the balance of forces. That's it. Okay, so this is the Navier-Stokes equation for an incompressible fluid. Okay. All right. So now when I say that this is written for incompressible fluid, there is always one equation that always follows the Navier-Stokes equation, and that's the equation of continuity, which is nothing but just that the velocity field is solenoidal, which means the gradient of velocity, the divergence of velocity field is equal to 0. And remember, when I say that I write the Navier-Stokes equation for an incompressible fluid, this means the continuity equation always follows the Navier-Stokes equation. That's it. Okay, so this is basically the NS equations, or the much celebrated Navier-Stokes equation that we use in fluid dynamics, where I would say the first term that you see, that this is the first term, it says it is nothing but the force due to inertia. And actually it is not force, it is force per unit volume, because if you calculate the dimension of this term, you will inevitably see that this is nothing but force per unit volume. So but crudely you can say that it is just in a unit volume, it just depicts what is the force due to inertia. It is something like this. Okay, and the term on the right, we have this term which is gradient of P. Okay, which is the, again, this is the force per unit volume due to pressure. So it is force due to pressure. And remember, when I say force in Navier-Stokes equation, it is the force that is exerted in a unit volume of fluid. That's the thing that I mean here. Okay, which means that the terms has a dimension of Newton per meter cube. That's the thing. So this is force due to pressure, and this term, that is the second term, it is mu times the Laplacian of the velocity field. Okay, this is called as the viscous forces. And the last term, the density times B, is the body force that we are, trying to understand. So this is the body force. Okay. So in a way, you can see that the Navier-Stokes equation is essentially a balance of force. So you can say that the inertia here is being, sorry, the inertia here is being balanced by the force due to pressure, the viscous force, and the body forces. So ultimately you can realize that you are essentially writing F equal to ma, which is the Newton's second law, in a Eulerian description, in an Eulerian description, to be precise. Okay, so that's what you are essentially doing it. But this is written, so F equal to ma, as I said, it is written in a Lagrangian frame. You are kind of depicting the same thing, the same principle, which is the balance of, so Newton's second law is nothing but, it just says that force equal to mass times acceleration. That's it. So you are just doing that, or actually this mass time acceleration is being depicted by this term in an Eulerian frame, and these are the net forces that you write in Newton's second law. Okay, and you are just doing that, you are just connecting that Lagrangian description uh, by this Eulerian description, which we call it the Navier-Stokes equation. And of course you are doing that by using the Reynolds transport theorem. That's what you are basically doing. Okay, but this is an essential description of the Eulerian frame. Sorry, and so this is an essential description of the Lagrangian frame in the, what to say, in the Lagrangian frame. Yeah, and you are writing this in Eulerian description. That's the thing that I want to portray here. Okay, all right. So you can appreciate here that the number of variables in Navier-Stokes equation is essentially 4, because in a 3D space, I have three components of velocity, for instance, ux, uy, and uz. And I also have an unknown, which is pressure, which means in order to evaluate these four unknowns, which are the three components of velocities, at least in a 3D space, and pressure, I need four equations basically. And we also have four equations, which means that is typically because although this equation seemingly, it seems to be just an equation, remember this is a vector equation. So I can write this equation for for three components, to be precise, of velocity. For instance, like ux, uy, and uz. Okay, and if I do that, I have three equations from this single vector equation, and I also have this continuity equation, which means total in a total I have four equations, and also I have a four unknown, where the three components of velocity are unknowns, and the pressure is an unknown. So four equations and four unknowns. So it's a closed system that we are dealing with. Okay, in when we are trying to solve when we are trying to basically solve the Navier-Stokes equation. Okay, so this is something that you need to realize. All right. So this is the this is a brief intro of the different terms that are involved in the Navier-Stokes equation. The more detailed analysis, you have already done this in the week's lecture. So we will just start off here by writing, by looking, just trying to derive the flow field for certain cases, for certain simplifying, I mean cases, where we can see that indeed closed form solutions of the Navier-Stokes equation, I mean by closed form, I mean closed form analytical solutions of the Navier-Stokes equations are possible to write down. And one such example we will do it now, which I think you can see it from your screen basically. But before that, we'll stop here for a couple of minutes. If you have any doubts involving, the Navier-Stokes equation that I wrote, or the constants and the variables and all those things, you can ask, or feel free to let me know. Okay. If no If no questions, let's try to understand and let's try to derive, I mean, to use the Navier-Stokes equation in trying to solve this problem. So this problem, I call this problem as pressure-driven flow between two parallel plates, with one of the plates moving with some uniform velocity, and the magnitude of this uniform velocity is u naught. So you can appreciate that it's kind of a superposition of the Couette flow, where you studied that there is just two plates, there isn't any pressure gradient, and one of the plate moves in one direction with a given velocity. And the other problem is that's the one part of the problem. The other problem is that the two plates are stationary and there is an applied pressure gradient. So you can see that this problem that I just now stated is kind of a linear superposition, or like, we'll see the word linear. So that's a careful term that we need to deal with, but it's kind of a superposition between, so it's a superposition of the Couette flow and the planar and the plane possible flow that you study. So we will prove that the solution of this problem will also be a linear superposition of these two simplifying problems, and that is possible, as we will see very shortly, because of the fact that the governing equations are linear. So if the governing equations are linear, I can use the method of superposition, which we will see very shortly, to basically derive closed form solution to the to complex problem, which can be broken into the simpler problems that I just now stated. But we'll see that later on. What we will do is, first we will start from scratch. We will solve these problems by using the Navier-Stokes equation and come out with the solution of the velocity profile. And this is something that they have asked us, the expression of the velocity profile and the volume flow rate. And at last we will see that the velocity profile that we wrote, this is indeed a linear superposition of the simplifying velocity profile of two problems. One, the Couette flow, where one of the plate moves with a given velocity, and two, the plane possible flow, where the plates are stationary but there is an applied pressure gradient. Okay, so I hope the idea is clear on, and the roadmap is clear. And we will see so that's the last part of this problem. So what we'll do is, we will start off with the Navier-Stokes equation, writing the Navier-Stokes equation for the given paradigm that we saw, derive an expression for the velocity profile, and they also asked us to evaluate the volume flow rate, and we will see that. And given these two cases, given by answering these two questions, we will see that the solution is indeed a linear superposition of the two simplifying problems. That is something that we will see, and at last we will argue that this linear superposition is possible because of the fact that your governing equations are linear. That's the idea. Okay, so what we will do is, as I said, we'll start off by writing the assumptions, because this is something that we always so that's the ritual that we always do while solving these kind of equation. So we'll start off by writing the assumptions. Okay, and these assumptions that we'll write, these are actually a part. So some of these are actually a part of your assignment. So you can take a close look at this, and you will get the answers to your assignments as well. Okay. All right. So so the first assumption that we will consider, we'll consider that the flow is steady. It's a steady flow. The second is that we'll consider the flow to be fully developed. I mean, these are the things that we have already saw it in the lecture classes, so we'll not elaborate much on this. Rather, we'll use this to basically solve the problem. That's the idea of these sessions, essentially. Okay, so the flow is fully developed. Okay. The third assumption is that it's an incompressible flow. Okay. Maybe you can write that there is no body force. That is, you will neglect the effects of gravity here. And you can also write that the flow is unidirectional, which means that there is just one component of velocity. Okay. So unidirectional flow. All right. So these are the assumptions that we'll use to basically we'll invoke these assumptions in the Navier-Stokes equation to try in evaluating the velocity profile for this given problem. I mean, that's the idea. Okay. All right. So if this is done, let's now start off by writing the equations and then invoking these assumptions. So the first, so the governing equations. Okay. All right. So we'll begin, by writing the continuity equation. So the first is the continuity equation. And it just says ki the divergence of velocity field is 0, because of the fact that we are assuming that the flow that it's an incompressible fluid or an incompressible flow, which means that the divergence of velocity field is 0. And if you write this in component form, you can, so that your del ux by del x plus del uy by del y plus del uz by del z is equals to 0. Okay, where ux, uy, and uz are the three components of the velocity that we just now wrote. For instance, like this velocity field that I wrote here, this velocity field is just ux ex plus uy ui plus uz ez. That's the thing. Okay. All right. Now, since we have assumed that it's a unidirectional flow, which means that this assumption says that I just have a non-zero ux component of velocity, because of the fact that the plate is moving in this direction, and I have a pressure gradient in the x direction, which means that the only possible direction along which the flow would actuate is the x direction. Okay, which means that my ux is non-zero, but since it's a unidirectional flow, my uy and uz is equals to 0. Okay, this means that my uz 0 and my uy is 0, which means from the continuity equation I can conclude that my del ux by del x is equal to 0. So what does it mean? It means that since del ux by del x equals 0, this means that my ux is not a function of x, is not a function of x. Okay, this is something that you get. It's a very important conclusion. This means that your ux is not a function of x. Okay, which means so there is something which is it's kind of an essential conclusion of the fully developed nature. So you can say that this is, so you can say that this implies that the flow is fully developed, something like this. But it's like, so it physically means that if you stand in any location in the channel, in any x location in the channel, you will see that your velocity profile is just the same. Okay, this is sometimes called as the translational invariance, which means that along the channel your velocity profile is not varying with the channel length, okay. So this del ux by del x equal to 0 means that your ux is not a function of x, which now means that the only possible case is that your ux is just a function of y. It cannot be a function of z, because we are kind of looking into, so it cannot, so it's like it cannot be a function of z because of the fact that we are neglecting the third dimension of this problem. Okay, we are assuming that the width is infinite. So it's an assumption. Actually, I need to write. So there is also one more assumption that I need to write in order to draw more clarity, that the width is infinitely large. So width is large basically, which means that my variables will not be a function of z. Okay, cannot be a three-dimensional variation that is possible, which now means that if u is not a function of x, at max ux is just a, so at max ux can be a function of y. That's the thing. Okay, so ux is a function of y. Remember, ux cannot be a function of time because we have already invoked the assumption of steady analysis. Okay, which means that my ux is just a function of y. That's it. That's the important conclusion that you can draw from the assumptions and from the continuity equation. Okay, so if ux is just a function of y, our next step is just to calculate this ux. That's the thing that we need, and this is sufficient to give us the velocity profile because all other velocity profiles ui and uz are just 0. Okay, all right. Any doubts till this point? Please let me know. Like, I mean, please feel free to like let me know. All right. Okay. But see, we haven't we just drew the conclusion that there is going to be just one component of velocity, which is just ux. It is just going to be a function of y, that is the cross length variation, as you can see from this figure. So your y is basically this. Okay, which just means now, it means that, so what does it mean? It now means that we drew this conclusion, but we still don't know what is ux. And for finding ux, we will go to the Navier-Stokes equation. That's it, and that's what we do. So the idea of solving the Navier-Stokes equation is to solve for its first primitive variable, and that's the velocity. Okay, the velocity field to be precise. So what we will do is we will start off with the x momentum equation, or the x component of the Navier-Stokes equation, and try to see how things go. Okay, so we'll write the x component of the Navier-Stokes equation. All right. So from this vector form of the Navier-Stokes equation, if you write the x component, your x component will basically look something like this. Okay. So the inertia, that is the term on the left, will be rho times del ux by del t plus, so that's the temporal term, plus ux del ux by del x plus uy del ux by del y plus uz del ux by del z. That's the inertia term. And then the terms on the right, we have the pressure gradient, which is minus dp by dx. Okay. Or maybe I should write it in general, maybe I should write it as del p by del x. And later on, we will see that pressure also varies just in the x direction. And we will see that very shortly. But let's for now, let us write it as del p by del x plus mu, the viscous term. So the viscous term is mu Laplacian of the velocity field. The Laplacian of the velocity field in 2D coordinate system will just give you del square ux by del x square plus del square ux by del y square plus what? Del square, sorry, del square ux by del z square. Okay. Plus, there is no body force, so we'll discard the body force term. Now, let's invoke all the assumptions that we wrote, okay? Since the flow is steady, my this term goes. I do not have, the y and z component of velocity, which means these terms, go to oblivion. I said that my ux is not a function of x, which means that this term is essentially 0. And my ux is also not a function of z because I assume that the width of the plate is very large. So there is very less or there is very less or there is no variation along the z direction. Okay, which now means that and of course, since ux is not a function of x, I can also write this term to be equal to 0. Which now means that the left hand side is just 0, and I have minus del p by del x plus mu del square ux by del y square. All right. Now, before going further into, analyzing or simplifying this problem, let's do one thing and write the y momentum equation. And we will see an important and a very important yet and a very important, and a very interesting conclusion from this, from the y momentum equation. Okay. So, so if I now write the y momentum equations, I repeat, we will analyze this equation, which is equation number 1. But before analyzing, let's write the y momentum equation and see something very interesting. Okay. So what we'll do is we'll write the y momentum equation, and the y momentum equation would look something like this. Okay, just how the x momentum, just how you wrote the x momentum equation. If you just follow, it will be just rho times this time it would be just del uy by del t, and the inertia term is just I mean the convective term is just ux del uy by del x plus uy del uy by del y plus uz del uz by del z, and then I have minus of del p by del y plus mu, what I have del square uy by del x square plus del square uy by del y square plus del square uz by, sorry, this is going to be uy del square uy by del z square. Okay. Now, if we invoke all the assumptions, I said that the flow is just unidirectional, which means that ui and uz, these are all 0. Okay. This should be ui. Okay. So if I invoke this assumption that I just have a non-zero x component of velocity, meaning that all the ui's and uz will be 0. This means that this term is just 0. This is 0. All these terms are just 0. Because of the fact that I don't have an uy, so the y momentum equation just boils down to the fact that my del p by del y is equal to 0. So this means that, so what does it mean? It means that my pressure, so it means that my pressure is not a function of y. So this pressure is not a function of y, which also means that my pressure is not a function of z because I have considered the width to be very large. We will not bother into going into the z dimension now, which now means that my pressure at max is a function of x. Okay, my pressure p is a function of x, which means that I can now replace this del p by del x as a ordinary derivative of dp by dx. That's the important conclusion, as what I was saying, that we could draw from the y momentum equation. Okay, so equation 1 now becomes, because of the fact that your pressure is just a function of x, so 1 now becomes 0 equal to minus dp by dx plus mu del square ux by del y square. All right, now let's try to understand this equation. So these are certain nuances that we get and we appreciate when we solve the Navier-Stokes equation, because these are very minor details that are so beautiful that you can appreciate how rich the Navier-Stokes equations are essentially. Okay, so now see, what we are doing is we are saying that my pressure is just a function of x. So what we are doing is I am just saying that this term is just a function of x, and I just now stated few time back that ux is a function of y, which means that this term, that the term that I wrote here, it is just some, let's say, f tilde of y. So what are we doing essentially? We are saying that a function of x plus a function of y is basically equal to 0. And when is it possible? Because this term is solely a function of y. We prove that because ux is not a function of x, which means that ux is just a function of y only. And we are saying that a function of y is equal to a function of x. This is only possible when these two things is equal to a constant, which means that the only possible scenario is that dp by dx has to be a constant. And that is only, and this is the only possible scenario when a function of x is equal to a function of y, or you can say that the function of x plus a function of y becomes equal to 0. So the conclusion is that dp by dx, so the conclusion that you can draw from here is that dp by dx has to be a constant. That's the only conclusion that you can draw from this point. Okay, so dp by dx is a constant. And this is essentially the case that is given in the problem, because I already stated that, come back to the problem statement. I already said that the flow is actuated by constant pressure gradient dp by dx. This dp by dx is nothing but it's just a constant. We can just write it as some g. Okay, and from the Navier-Stokes equation we have proved that this dp by dx, it has to be a constant if we invoke all these assumptions into the analysis. Okay, so these are certain nuances of that we get when we start the Navier-Stokes equation from scratch, and try to analyze each step carefully. Okay, so I can now write it as, so I can just now write it as this dp by dx. So this I can now write it as some g minus dp by dx to be some g. Okay, all right. Or I can say that okay, I can say that dp by dx is g, so this becomes minus g, whatever. So plus and minus is just so since g is just an arbitrary constant, you can include the plus and plus or a minus. You can include the minus or you can exclude the minus. That's up to you. But I will just say that dp by dx is just g. That's the thing. Okay, and I hope you have realized that why dp by dx, the only possible scenario of dp by dx is that it has to be a constant. Okay, all right. because this cannot be constant. If this is constant, this means that your velocity profile is constant, which is not the case, because we have proved that ux is indeed a function of y. Okay, all right. So I can write down this as now 0 equal to minus g plus mu times del square but ux by del y square. All right, so this can now be written as what? I can write it as, all right. And now see, since ux is just a function of y only, I can replace these partial derivatives with the ordinary derivatives as d2 ux by dy square. This is typically because ux, as we proved, is just a function of y. It is not a function of x, it is not a function of z, it is also not a function of time. Okay, So I can now write it as d2ux by dy2 to be equal to g by mu. Okay, so that's it, guys. That's the ODE. So you can see that this is an ODE that we need to solve in order to get the velocity profile ux. Sorry. So this is the ODE that we need to solve. I'll name it as what? So I think I have introduced some equations or what? Let's see. This is equation 1. Let's say I call it as equation 2. And I name it as equation 3. Okay. So we just need to solve equation 3. We just need to solve this ODE. You can see this is, so basically this is a second order ODE. It's linear, of course, and it is non-homogeneous, because if you put ux to be equal to 0, you still get a non-zero, right hand side. Okay. So in order to solve this ODE, as you know, we need to basically see the boundary conditions. So let's quickly see the boundary conditions. So the boundary conditions are that. So what are the boundary conditions? So that comes from the physical problem, right? See, there is a plate. So the upper plate is moving with u naught, and the lower plate is fixed. So we have two. So outrightly, we have just two boundary conditions. Okay, and that is sufficient because it's a second order ODE that we are kind of solving. Okay, so and we have considered the axis system to be at the bottom of the plate, which means the two boundary conditions that we can draw from this point is that ux at y equals to 0 is 0. That is because of the fact that your lower plate is fixed, and it is a consequence of the no slip boundary condition that you guys already know. Okay, and the second boundary condition is that my ux at y equal to h is u naught, which is the velocity of the plate, and these two are the no slip uh, boundary condition. All right. There is also something which is known as a no penetration boundary condition, which dictates so as to why ui is 0, because of the fact that if you it's just that since these plates are solid, fluid cannot basically go you know through this, which means that if you basically write ui, so ui is basically 0 at these and these point. Okay, and you have proved that ui cannot basically vary in this direction, which means that the only solution for ui, if you just write it, the only solution for ui in this case is that ui is 0, and this you can argue from the no penetration boundary condition. But I hope you already understood this. So I just skip this part, but at least you can realize that this comes from the no penetration boundary condition actually. Okay. All right. Okay, so that's it. We just now need to basically integrate this using these two boundary conditions to get the velocity profile. So let's see what do we get. So if we integrate equation 3, so we'll just integrate equation 3. So if we integrate this, if we integrate it once with respect to y, we get dux by dy, and this becomes gy by mu plus some constant, let's say c1. And then again, if we integrate it once again, if we just integrate it once again, you will get ux of y as g by 2 mu y square plus c1y plus c2. That's it. Where c1 and c2 are the constants of integration, we will derive from by applying these boundary conditions. Okay, so let's apply this and try to find out what is c1 and c2. So we know that ux at y equals to 0 is 0, which means that, so if you impose this condition, you will see that your c2 comes out to be equals to 0, and we know that ux at y equal to h is basically u naught, and if you impose this, what you will get is u naught equal to g by 2 mu h square plus c1h. Okay, and from here, if you want to calculate what is c1, your c1h would become what? U naught minus of g by 2 mu h square. Okay, and c1 is just u naught by h minus g by 2 mu h. And what you need to do is you just need to now substitute this value of C1 into the governing equation, and of course C2 into this governing equation as well, which means that you will just get what you will get. You will just get ux as a function of y as g by 2 mu y square, okay, plus C1 times y. C1 is this u naught by h minus g by 2 mu h, okay. Remember, you are multiplying this with y, so there would be this y, and C2 is of course equal to 0. All right. So what I will now do is I will write this equation in this form, and we'll see a very interesting phenomena that is happening here. Okay, and it's a physical phenomenon to be precise. So what I'll do is I will I'll segregate these two terms in the bracket. This term is just g by 2 mu y square. The other term I'll write it as minus g by 2 mu hy plus u naught y by h. And then I will write this term as u by x, and I'll take this g by 2 mu common, and this would be y square minus yh plus u naught y by h. So this is the total velocity profile that the question has asked us to find. But that is what the math said us. We can draw a very important and yet a very interesting conclusion from this velocity profile. See, if we have a close look, this bit, okay, sorry, if we just have a close look, this bit is the solution to the flow when the two plates are stationary and there is just an applied pressure gradient, which we call it as the plane possible flow. So this is the solution to the plane possible flow. And the second part, which is this, maybe I'll write it some different color. The second part, which is this, is the solution when there is no pressure gradient, but you are actuating the fluid by moving the upper plate with some velocity u naught, which is nothing but the Couette flow. Okay, so this is the solution to the Couette flow. And our problem, as I said, since it is so what is our problem? Our problem is that there is an applied pressure gradient, also the upper plate is moving with some u naught. So the solution to our problem, as you can see, is actually a linear superposition of the solution to the plane possible flow plus the solution to the Couette flow. And as I said, this is possible because the governing equation, which is given by this equation 3, is linear. So since the governing equation is linear, okay, the solution to this complex problem, which involved the the mixture of these two so it's a mixture of the plane possible flow plus the Couette flow, and the solution is actually a linear superposition of the solution of the individual problems. Okay, and this is possible because your governing equation is essentially linear. Okay, and this is something that you must realize through this exercise, that is some I mean, that I would say is the most important thing that you should realize, okay, apart from the math that we did here. So I repeat, so it's the fact that since your governing equation is linear, your solution will also be a linear superposition of the simplified problems, which you already solved in the lecture classes essentially. So now, if you are aware of that, you don't need to do this entire math. You can say that since the governing equation is linear, the solution to this problem is essentially a linear superposition of the solution of the plane possible flow and the solution of the Couette flow. This is something that you must realize, when we have these kind of governing equations, to be precise. All right. So we are left. So before proceeding, any questions on this? Please feel free to let me know. All right. I hope you have understood to uh, the fact that I just now stated. We are still left to do one more thing. So what we need is the B part is that we also need to calculate the volume flow rate. Okay. So how do we do that? Okay, so let's calculate the volume flow rate, and this is easy. This is not just it's not that difficult once we know the velocity profile. So what we'll do is we know that the lower plate is fixed. There is an upper plate which is moving, but the important bit is that I have a velocity profile which is varying along y. So what I will do is, in order to calculate the volume flow rate, I will first calculate the differential volume flow rate moving through a differential volume. And for that, what I will do is I will choose, and since this is my axis, this is my x, and this is my y. So what I will do is I'll pick a generic y, as we do in so this is a way to handle varying quantities typically. So we'll choose a generic y, and I'll choose a small, what to say. Okay, so what I will do is in this generic y, I'll choose a small strip, let's say of this form. I'll choose a small strip of this form, which has got a thickness of dy. Okay, this bit is dy. And let us consider for this instant that the width basically goes something like this, because of the fact that your plates are also, having some width. And I said that the width is infinitely long, which means that this goes basically to a very large length. Okay, and we will just consider this differential volume that I just now stated. Okay, so through this differential volume, the idea is that we will calculate what will be the volume flow rate. Because of the fact that your velocity is varying along y, I need to choose the differential volume and calculate the volume flow rate that is precisely, uh, moving out from this differential volume. Okay, so so as I said, the volume flow rate that is moving out from this differential volume, I'll denote it as dq. It is just going to be the velocity times the area. The area is going to be the width. So what is the area? Area is going to be this width multiplied by this height. Basically, it's going to be this width multiplied by this height, because this is the area through which the fluid is basically coming out. I'll say it with some different color. Let's say this is some. So this is precisely the area, and of course this area essentially extends because of the fact that your width is very large. Okay, but for the sake of analysis, we'll consider that the width is basically b. You can assume that your b is very large. This is something that you can assume. So for the sake of this analysis, we'll just assume that your width is precisely b. Okay, which means that your area is going to be, so your differential volume flow rate is going to be the velocity, which is ux of y, times area, which is b times dy. I hope you can understand this from this diagram, to be precise. So for the sake of solving this problem, we'll consider that this width is basically b. You can also consider the width to be unity, or what you can do is you can calculate the volume flow rate per unit width. So you all you need to do is you just need to divide this equation by b. That's the thing that you need to do. Anything is fine in this context. Okay, but just for the ease of understanding, I'm considering a generic width, which is b. You can assume that this width b is very large with respect to the length of the plates, or this thickness, not the length or this thickness. The assumption that we have invoked is that this b is very much larger than this h, where this h is basically this height. All right, that's the thing that we're doing. So so this is precisely the differential volume flow rate. Okay, and in order to get the total volume flow rate, what I will do is I'll integrate this from 0 to h, which is the height of the channel. So this will be an integration from 0 to h ux of y v dy. That's it. And we already know ux, right? Ux is just this. So we just need to do this integration. That's the only thing that we need to do. Okay. So if I just write down this expression for ux, let's do this, and let's do this integration, and let's see what the volume flow rate would come out to be. So this Q is basically this integration. Ux is just this term. Okay, Ux is just this. So let's write it down. It is g by 2 mu y square minus yh. It is g by 2 mu y square minus yh. Okay, plus u naught y by h. This is my ux, and I need to integrate it with respect to y. Let's for the time being calculate what is q by v, which is the volume flow rate per unit width, and this is just this integration, integral 0 to h g by 2 mu y square minus yh, okay, plus plus what this term u naught y by h, and then we are integrating this with respect to dy. All right, so we just need to do this integration. Let's do it. It is just q by v, and this is, so the first two term will just give us integral 0 to h. G by 2 mu is just a constant, so it will come out, and it is just an integral from from 0 to h y square minus yh dy, plus the second term is just u naught by h integral 0 to h y dy. We are just segregating the two terms here. Okay, that's all that we are doing. So this would be what? This would be q by v, g by 2 mu, and y square, integration of y square is y cube by 3, and you put the limit, it will be h cube by 3 minus integral of y is going to be y square by 2, which means it is going to be h square by 2, but there is already an h here, which means it would just be h cube by 2. That's it. I hope you got the step. It is just the math. You can just do it at your end, and I think you are now experts of these things at this point, at this level where you are studying this course. Okay, so it's just the math that we are doing, and the other term is just going to be y square by 2, but there is already a h in the denominator, so it is just going to be u naught h by 2, because of the fact that this integration would give us h square by 2, but there is an h here, so it is just going to be u naught h by 2. All right, so I think that's the thing. And if you do this integration, sorry, if you do this difference, this h cube by 3 minus h cube by 2 will just give you h cube by 6, which means that your volume flow rate per unit width, okay, is just going to be g by 2 mu h cube by 6, okay. Precisely, it will going to be minus h cube by 6, typically because this term is essentially less than this term. So it is going to be minus h cube by 6 plus, you know, u naught h by 2. All right, so that's it. That's the volume flow rate that that the question has asked us to find. Okay, so that's it, guys. That's the thing that that we are asked now. So we can actually look for a very special case in this solution. Okay, and let's see. So it's like, can you see this term? If you see this term, okay, this term, so let's have a look at this term. Okay, since h is positive, this term is essentially n, and I'm assuming that g is greater than 0, because there is a minus g here, which means this term is always negative because there is a minus sign here. On the other hand, if my plate have a positive ux velocity, which means this term is positive, which means that under a special case, you know, if there is a special case for which my q happens to be equal to 0, see, remember I'm telling this is a special case, then I can just say that g by 2 mu, okay, by g by 2 mu h cube by 6, this has to be exactly equal to u naught h by 2. This is because of the fact that this term I am considering to be 0, which means I have a very special velocity, okay, which is equal to, so I have a very special velocity of the plate u naught, which is equal to gh square, okay, by 6 mu. Okay, so it's like if you drive the plate with this velocity, your net volume flow rate in the system is zero. And it's a very interesting thing that that you can conclude, that if you move the plate with this velocity gc, mu is a constant for water, let's say mu is 10 to the power minus 3 pascal second. H you can consider to be a channel height, let's say it is 1 mm. Okay, if you substitute this, and this is the pressure gradient dp by dx, you can consider anything. Let's say my pressure gradient is what, you can just consider any value for this pressure gradient. So if you so the meaning is, you know all these things value, and if by chance that your plate velocity becomes equal to this velocity, your net volume flow rate in the system would be zero. That's the important conclusion that you can determine. So this is the condition, I would say this is the condition for no, or for zero volume flow rate, for zero volume flow rate. Okay, I hope you I hope you have appreciated this thing, that if you move the plate with this velocity, your net volume flow rate in the system is just zero. And that is something, very interesting, because you so remember, even if the net volume flow rate is zero, your flow field will not be equal to zero. It's just that the two forces basically cancels each other. It's the net flow that basically is zero. That's the thing that you can appreciate from this. Okay, I hope this is clear. And let's see, like, if there is anything else to discuss. Okay. All right, so that's it, guys. So we have finished this problem, and this is one of an important problem. This is because it gave us many insights. The first insight is that we solved we so what we did, we looked into the assumptions that are involved in these kind of unidirectional, rectilinear flows. And then we saw that using these assumptions, we simplified the Navier-Stokes equation. We saw the continuity equation. We simplified the Navier-Stokes equation and argued certain nuances from this Navier-Stokes equation. And finally, we integrated this using the boundary conditions to evaluate the flow field. Okay, and we saw that after evaluating the flow field, we saw that the flow field is essentially a linear superposition of the two simpler cases, which is the cases for which is the solution for the plane possible flow and the Couette flow. Okay, and and then we also evaluated the volume flow rate. We also saw that the volume flow rate basically comes out to be something like this. And then we also argued that what should be the plate velocity such that this q, the volume flow rate, basically turns out to be equals to zero. Okay, so these are the things that we just now solved. So we'll end this class by solving a very simple problem. That is basically by solving another very simple problem. But before that, if you have any questions, you can ask. So we'll end this by solving a very simple problem on Couette flow to basically calculate. So we'll see the concept of shear stress, and then we will just call it a day for this session. Okay, but before that, if you have any questions on this, please feel free to let me know. All right, if no questions, then let's finish it up by just solving this simple problem. So this is just the Couette flow where the upper plate is moving with some velocity u naught. All you require to do is, given this height of the plate and given the fluid properties, you are just asked to calculate the shear stress, and that's it. That's all that you need to do. And we'll consider a 2D system, meaning that the width is very large, so we'll not bother about the variation in along the width, as what we did very recently. Okay, so so the way how we can basically calculate the shear stress is that, because we know that the shear stress, that is the deviatory component of stress, it is also known as the deviatory component. And in this case, it will just be the tau xy, because we just have this xy plane here, and this is going to be mu del. So you already know this, so it is just going to be mu times del u by, sorry, it's just going to be mu times del u by del y plus del v by del x. But you know that for a Couette flow, so since this is a Couette flow, you already know that your velocity profile u is just a function of y, and it is of these from u naught y by h. This We already you derive this in class, and we also derive this here from this solution, which is basically this. Okay, which means, so what does it mean? It means that I don't have this v component of velocity. This is just 0. And for the shear stress, I just need to evaluate this term, which is mu times del u by del y. Remember, this is ux essentially. I shouldn't write it as v, because just to keep the notation same, this is just del ux by del y, and this should be del uy by del x. And I said that the y component of velocity, which is uy, is 0 here. So this just becomes mu times del ux by del x, and I know that for a quick flow, ux is just u naught y by h, which means that del ux by del y is just u naught by h. And if you just substitute it here, okay, your shear stress tau xy in the fluid would just become mu times, it just becomes mu times u naught by h, which means your shear stress is essentially a constant. That's the thing that you can infer. So for example, if I draw the velocity profile here is just u naught y by h, which means that the velocity profile is 0 at the bottom plate, and it is u naught y by h, and it is u naught at the far plate. This is basically u naught, and the variation is linear because you can appreciate from this solution, which means that I have a linear variation of the velocity. So this is how the velocity field will essentially vary for this quick flow, and it is just u naught y by h. That is something that we saw. But if I draw the shear stress variation, it is just a constant, because the shear stress variation is just something like this, just this, and it is just this. It is just a constant that we are kind of doing. So this is how your your shear stress will basically vary. And I mean, this is the variation of tau w basically, or tau xy to be precise. So the shear stress at the so the shear stress at the upper and the lower plate is equal to the shear stress of the fluid, because of the fact that your shear stress is constant, and it is nothing but u naught mu times u naught y by h. And this is because of the fact that, see, you can infer that because your stress is basically the gradient of velocity. Uh, and in this case, it's the derivative of velocity with respect to y, derivative of the x component of velocity with respect to y for this very particular case. And since you know that your ux varies linearly with y, its gradient is just going to be a constant, and that's why for quick flows your shear stress is basically constant throughout the channel, and it is equal to the shear stress at any intermediate position in the channel is equal to the shear stress at the top and the shear stress at the bottom. But remember, if it's a plain possible flow, your velocity profile is parabolic, which means that your shear stress will now vary. And you can show that in plain possible flow, your shear stress is maximum at the walls, and it is minimum it's basically minimum at the center. This is something that you can also show. That all comes because if you know the velocity profile, just differentiate that with respect to y for unidirectional flows like this, and you will basically get the shear stress. Okay. And this problem is supposed to just give you a flavor of how to just calculate the shear stress, and this is something that I wish to show you. All right, so we end the discussion on unidirectional rectilinear flows on this part. Uh, so we saw basically certain important problems. So we saw the linear superposition of the problems that you already saw in the lecture series, but we saw that by superimposing this problem, I made a problem which basically consists of the Couette flow and the plane parabolic flow, and then we saw that we started off from the basic Navier-Stokes equation, and we proved that the solutions are also linearly superimposed. This is again because of the fact that your governing equation is linear. Okay, and we will see the consequences of similar kind when we learn something which is known as the creeping flow, where the governing equations are linear, and we'll see that the governing equations which satisfies creeping flows, these are known as the Stokes equation, the Stokes flow equation, and we'll saw that since those governing equations are also linear, we will see certain important consequences of the linearity there when we learn creeping flows basically. Okay, but that's the idea. We saw this today, and then we also saw how to calculate the volume flow rate and also the shear stress of flows that we know, basically the velocity profiles that we know. Okay, so that's it for this session. We are about to finish our time. But I'll stop. I'll wait here for a couple of minutes. If you have any doubts associated with this week or the previous week, or any or any doubts associated with the assignments, you can ask basically, and I'll be happy to clarify your questions. If not, then we'll meet at the same time in the next week, in the same link, of course, from 3 to 5, as you already know, and we'll see the contents of the next week. So in next week, we'll discuss something which is known as the Hagen possible flow, that is the flow through pipes. And thereafter, we'll look into certain more complex analytical solutions to the Navier-Stokes equation. What happens when, when time comes into a picture, or when the space is now 2D instead of 1D, is something. So these are some things that we'll see in the subsequent weeks that follows. Okay. But so this is the agenda for the next week. But if you have any questions, you can always ask me. So you can ask here, or you can post it in the discussion forum. And since there are no questions now, we'll call it a day. Thank you for being here, or thank you for listening to these videos. These are also recorded, and you'll find the recordings in the website and also on YouTube. And I thank you for attending the sessions. Please give your feedback. I think you are asked every week on that. Please try to feel that feedback, because it gives us a message on how on which aspects the improvements are required. And it helps, it also helps people like me to devise the strategy of teaching these things in a much better way. Okay, so please fill the feedback form. That's the idea. And I thank you very much for joining. We'll call it a day here, and see you next week.